For the warm-up today, we need to look at the process for making solutions. So we've talked about this from a mathematical perspective and how to do the calculations, which we will look at in a minute. But we also need to talk about the actual process for making these. So what glassware is included, what that looks like in terms of the steps that you're going to take to make these different solutions. And we'll look at the first one. Describe the process for making a solution of 250 milliliters of 0.30 molar sodium hydroxide from 6 molar sodium hydroxide. So what we should see here is that we're starting with a 6 molar solution and we're ending with a 0.3 molar solution. So this is clearly a dilution problem in which we can use the dilution equation. Remember, our dilution equation is M1 V1 equals M2 V2, because we have to remember that moles before the dilution are the same as the number of moles after the dilution. The only thing that's changed is the amount of solvent, in this case water, but the number of moles remains the same. So we can just plug in our values for our first molarity, and we can do this either way as long as we make sure we are pairing the appropriate values together. We can say that the molarity is 6. Since we're talking about before, it makes sense that we would use this as molarity 1 times X, because we need to know what volume of that 6 molar solution we would need to be able to dilute this solution to the suggested molarity, which is 0.30 molar. And then we're multiplying that by the volume that we need, which is 250 milliliters. Now we don't need to convert this to liters, because as long as we're putting milliliters into the equation, that's exactly what we're going to get out as a result. So if we plug this into our calculator, we're actually doing 0.30 times 250 and dividing that by 6, because the idea is that we're isolating that X. And when we do that, divide both sides by 6, we get that X equals 12.5 milliliters, which means we need 12.5 milliliters of a 6 molar solution. So what is that going to look like in terms of the process? So we have equipment that looks like this. Over here, this says stock solution. So you're going to start by putting the desired amount of stock solution into what's called a volumetric flask. And this volumetric flask is calibrated to this point. You can just barely see that little line on there. And what that means is you're going to take a volumetric flask that is the size of the final solution that you're looking for. So in this case, since we're making 250 milliliters, we need a 250 milliliter volumetric flask. We've already determined how much of the more concentrated solution we need. So we are starting with 12.5 milliliters of our stock solution. So if this is our stock solution, we're going to use a pipette to withdraw 12.5 milliliters and place that 12.5 milliliters in the bottom of our volumetric flask. Now, we don't need to worry about the actual calculation of how much water we're going to add, because this volumetric flask is calibrated. So what that means is I'm going to add water, specifically distilled water, to avoid introducing any impurities into this solution. I'm going to add distilled water to the mark. And when I do that, I know I will end up with exactly 250 milliliters of solution, and I will have it diluted to the appropriate molarity as my calculation told me I needed to do. So the first thing you're going to do is dispense your stock solution, the amount that was determined in the calculation, and then you're going to fill to the line with distilled water. Now, as you do this, you're going to be creating a bit of a concentration gradient where the more concentrated solution is in the bottom, and then as you go up, it becomes less and less concentrated. So just adding the water isn't enough. We have to mix it. So the final step would be then to cap your volumetric flask and invert it or turn it upside down several times until it's homogeneous, or until it has the appearance of being the same throughout. The next type of solution we're asked to make is a little bit different. We're told we need 1 liter of a 1 molar NaCl solution, but in this case, we're not given the value of the molarity of a stock solution. So we know in this case, we're not diluting. We cannot use the dilution equation to figure this out. We're missing a variable. Instead, we have to know that if we're making a solution of an ionic solid, if it's not already from a higher molarity solution, we need to look at that as a solid that would need to be weighed out. So remember, ionic compounds are solid at room temperature. So what we need to do is figure out how many grams of this ionic solid we would need to weigh out to make this solution. So we know we need 1 liter of this solution. So that's the piece of information that we start with. For the next step, we're just using conversion factors to be able to convert from liters to moles. And we're able to do this because we have a molarity of sodium chloride. The desired molarity is 1 mole per 1 liter, which is what this 1 molar told us. And then the last step is going from moles, and remember we're talking about moles of NaCl, 2 grams of NaCl. And then from here, we need to determine the molar mass of NaCl. So remember, we do this by looking up each of the individual elements from the periodic table and their corresponding molar masses. And what we would find is that the molar mass of NaCl is 58.44 grams per 1 mole. We can stop here because now we have a mass of sodium chloride that needs to be weighed out to make this solution. Notice everything in here is a 1. So the answer to this is going to be 58.44 grams of NaCl. This is the amount of solid sodium chloride I need to weigh out to make this solution. The process uses similar equipment. The only thing that's missing is an original stock solution to dilute from. And since this is not a dilution problem, we don't have to worry about that. So what we're doing is using that same piece of equipment, that same volumetric flask that's calibrated. And in this case, the line we're calibrating to is right there. So what we're going to do is weigh out 58.44 grams of solid sodium chloride and then add that to the bottom of a volumetric flask. Now we're going to add just a little bit of distilled water, just enough to cover the sample and be able to have it dissolve. The more water you put in there, the more difficult it is to dissolve a solid. So we're just going to add enough water to be able to dissolve the solid. And then when we see that it has a homogeneous appearance, then we're going to fill it with water to the mark. And then when we do that, we know we have the exact amount of solution that we need. Since in this case, we were asked for a 1 liters of this solution, we're going to use a 1 liter volumetric flask. So as long as we fill it up to that mark, we know we have exactly 1 liters of solution. Remember, the final step is always to make sure the entire solution is homogeneous, because even though this part originally looked like a homogeneous mixture, when we put it in here, we could still end up with a concentration gradient, more concentrated at the bottom and then working its way up to the top to be less and less concentrated. So what we want to do is then make sure that we have a cap on this and then invert it. Just turn it up and down several times until the whole appearance of this whole solution is the same and homogeneous. The first question from the homework asks us to calculate the molarity in each of these situations. In the first situation, we're given 0.5 moles of NaCl and 0.2 liters of solution prepared. Remember, molarity, big M, equals moles per liter. So all that's necessary for us to do in each of these situations is divide the number of moles by the liters. So in the first case, 0.50 divided by 0.2 gives us 2.5 molar NaOH. In the second one, 0.75 moles of NaCl divided by 0.3 liters of solution again gives us 2.5 molar NaOH. In the second problem, standard solutions of calcium ion used to test for water hardness are prepared by dissolving pure calcium carbonate in dilute hydrochloric acid. 1.745 grams of calcium carbonate is placed in a 250 milliliter volumetric flask. Then the solution is diluted to the calibration mark of the volumetric flask. Calculate the resulting molarity. What we need to do first is figure out how many moles of calcium carbonate we have, because we need to be able to calculate the molarity of this solution, or rather the ions in this solution. So we have 1.745 grams of calcium carbonate, and then we do a quick conversion using molar mass to get us to moles. That gives us 0.01743 moles of calcium carbonate. Remember, this is moles of calcium carbonate. This is not moles, these are not moles of the calcium ion, but we can do a quick balanced equation to determine how the number of moles of calcium carbonate relate to the number of moles of calcium ion. And we can see in the balanced equation that because it's a 1-to-1 ratio, the number of moles is going to be the same. So we are going to use 0.01743 moles of calcium ion and divide that by the total number of liters of solution, which is 0.250. Don't forget to do that conversion. Notice they gave us 250 milliliters, but we need to be able to convert that to liters to be able to calculate molarity. So by dividing 0.01743 by 0.250, we get 0.06972 molar calcium ion. The next one asks us how many moles. There's a couple different ways you can look at this. The first is through unit conversion. We have 10 liters of solution. Liters of solution is on the bottom, and then we can use the molarity to convert to moles, 0.550 molar. Remember, 0.550 molar is the same thing as saying 0.550 moles per liter. We can do that quick math and get 5.5 moles of NaHCO3, or we can look at this when we were looking at the dilution equation. We said that volume times molarity equals the number of moles. So we can use that same logic here and just multiply 10 by 0.550, and that gives us the number of moles. And this should actually be moles instead of molarity. Applying the same logic to B, we get 2.125, and again, moles of acetic acid. In the next one, we're calculating the new molarity that results when one solution is diluted. So this is just a quick M1V1, M2V2. Remember, it doesn't matter which one is 1 and which one is 2 as long as you pair them together. So we get 0.0446 molar HCl in the first problem and 0.127 molar HCl in the second problem, following exactly the same solving technique. For the next one, given the following molarities of the concentrated acids, determine how many milliliters of each concentrated acid would be required to prepare 225 milliliters of a 3 molar solution of the acid. The only thing that's changing in each of these cases is the original molarity. The rest of the problem is exactly the same. We are still doing a dilution here because moles before equals moles after, so it's still M1V1, M2V2. So we can see for the first one, we get 55.79. For the second one, the first value changes, all of the other information is the same. So now we get 42.45 milliliters of nitric acid. And then for the last one, again, a different starting value, which gives us 37.5 milliliters of H2SO4. For our last homework problem, it is yet another dilution problem. So we've been given an initial molarity, we've been given the desired molarity, and the desired volume. So again, we're looking at M1V1 equals M2V2. But in this case, we're asked to describe how the student could prepare the solution. So we know we're working with 6.21 milliliters of NaOH, but what does that process look like? Remember, you're going to start with 6.2. So we're starting with 6.21 milliliters of our concentrated solution, which is approximately 3.02 molar. We are then distributing that dispensing that 6.21 milliliters of sodium hydroxide into a volumetric flask. And remember, that volumetric flask needs to be the size of the total solution that we need as a result. So we will be dispensing 6.21 milliliters of sodium hydroxide into a 125 milliliter volumetric flask. At this point, you're filling it to the line with water, capping and inverting to mix. And that's how you make your solution. For section 14.6, we're using the same calculations, we're just taking everything one step further. So our two aims for this section are to understand the strategy for solving stoichiometric problems for solution reactions and to explain the process of solution making, which we already looked at in the warm-up for today's lesson. So really we're just looking at the stoichiometric aspects of solutions and their calculations. So just a quick review of the steps for solving solution stoichiometry problems. Remember, the first step is to write the balanced equation. Remember, stoichiometry ultimately refers to the coefficients in the balanced equation, and we can't use those unless we know what they are. So we have to write the balanced equation first. The second step is to calculate the mass of product formed. So whatever information we're given about the reactant, we use stoichiometry to be able to convert from moles of reactant to moles of product. And then once we're in moles of product, we can use the molar mass to convert to grams of product. The last step is to determine the limiting reactant. So if we're given two different products or one product and two different amounts of reactants, we need to figure out how much product comes from both of those reactants. And then we are able to compare them and choose the smaller one because that one is going to limit how much product I can get. So for a sample problem, we're asked to calculate the mass of silver chloride formed when 12 grams of sodium chloride is added to 1.50 liters of a 0.10 molar silver nitrate solution. There is a lot going on in this problem, but what we need to do first is to balance the equation. We have enough information to be able to do that. So our first reactant is sodium chloride, and that is combining with silver nitrate. It's telling us that sodium chloride is added to silver nitrate. It's giving us one of the products, and one of those products is silver chloride. And then we can see we've already used the silver and the chlorine, so what we need to do now is we looked at this in chapter 6 when we were talking about double replacement reactions, is to switch partners. And what we end up with as our other product is sodium nitrate. So what we care about here is the mass of silver chloride formed. That's ultimately what we're going to be calculating. Don't forget we need to include states. And if we do this, we can see that what is solid is going to precipitate out of solution. And that's the only product we can actually weigh as a result of the mixture of sodium chloride and silver nitrate, because sodium nitrate is aqueous and still ends up in solution. So we're not able to physically weigh that sample. Now we need to balance this equation. So we can see that in fact it's already balanced. Everything is a 1-to-1-to-1 ratio. Step 2 is to calculate the mass of product formed from each reactant. We have information about both reactants, so using a little stoichiometry practice, we're able to do this. So we're starting with 1.50 liters of silver nitrate. Remember, before we can figure out how much product is formed, we need to convert two products. We're in reactants, so we need to be able to get to moles of reactant, so we can use the coefficients to go from moles of reactant to moles of product. So the first thing we need to do is to convert from liters of silver nitrate to moles of silver nitrate. Once we're in moles of silver nitrate, remember this is given to us through the molarity right here, because molar just means moles per liter. It's just a conversion factor. Once we're in moles of silver nitrate, we can go from moles of silver nitrate to moles of silver chloride, again using the coefficients in the balanced equation. And then our last step, since we're asked to calculate the mass of product, is to use the molar mass of silver chloride. And if we looked at our periodic table and found the corresponding molar masses, we would be adding up the mass of one silver and one chlorine atom, which means we have 143.35 grams of silver chloride. All we have in the denominator are ones, so the math that we're plugging into our calculator is 1.5 times 0.1 times 143.35, just all of those numbers across the top. And what we get is 21.5 grams of silver chloride. We can't stop here because we don't know if our other reactant is limiting or not. So we have to use the information given from the other reactant to be able to determine how much silver chloride is formed from that specific reactant. So this time, we're going to start with 12.0 grams of sodium chloride. We're going to go through the same process, except this time we need to use the molar mass of silver chloride to be able to convert to moles. Molar mass of silver chloride, as we saw in a previous example, was 58.44 grams per mole. Now that we're in moles of sodium chloride, we can go from moles of sodium chloride to moles of silver chloride using, again, the coefficients in the balanced equation. This is, again, a 1-to-1 ratio because all of our coefficients were 1. Our final step is to convert from moles of silver chloride to grams of silver chloride because, again, the problem was asking me to calculate the mass of silver chloride formed, so I need to go all the way to the end. This time, I have 12 and 143.35 on top and 58.44 on the bottom. So I'm going to be multiplying 12 by 143.35 and dividing that by 58.44. And what I get here is 29.4 grams of silver chloride. Step 3, my last step, is to determine the limiting reactant and product formed. Remember, what a lot of people want to do is add these two values of product together, but we don't want to do that. We have to choose the one that's smaller. The one that's smaller is 21.5 grams of silver chloride, and that means that silver nitrate is our limiting reactant. For our last section, section 14.7, we're going to learn to do calculations involved in acid-base reactions. And these are actually pretty simple because we can use a method we've talked about already to be able to solve these problems. What volume of a 0.100 molar HCl solution must be used to neutralize 25 milliliters of a 0.350 molar solution of NaOH? So the first thing we have to do is recognize that we have this word that we haven't seen before, and the word is neutralize. Neutralize we can think of as canceling out. We know if something is neutralizing something else, it is canceling out its effects, and that's what we want to look at here. But what we need to know is that neutralize is referring to the number of moles that are canceling each other out. So when a base has a certain number of moles and the base is neutralized by an acid, that means the number of moles are equal. And the other thing is, what is an acid and what is a base? So we know our HCl is our acid because we know the name of this compound is hydrochloric acid. Sodium hydroxide is our base, and we know that because it contains this OH group at the end of it. That is the characteristic anion of a base. So the first thing we need to do is write out a balanced equation because we can use stoichiometry to solve this problem. So we have HCl and NaOH, and following our double replacement process for predicting products, we're just going to switch the cations. And what we end up with is NaCl and H2O. We need the states and we need to balance the equation. So we know HCl, all acids are aqueous. We know if we're talking about a solution of sodium hydroxide, that refers to an aqueous compound. NaCl is also aqueous, and water is liquid because we're talking about pure water in this case. As far as balancing, again, we see everything as a 1-to-1 ratio, which makes the calculation pretty simple. So what we want to do is calculate from the volume of sodium hydroxide that we've been given, the volume of hydrochloric acid that will result. So notice I'm starting far over on the page because this is quite a lengthy conversion, but I will show you a shortcut in a minute. Starting with 25 milliliters of sodium hydroxide, we know that for every 1,000 milliliters of sodium hydroxide, we have 1 liter. So this is just a milliliter to liter conversion. The next step, using the molarity, we can go from liters to moles. They told us in the problem that we had a 0.350 molar solution, which means 0.350 moles of sodium hydroxide per liter of sodium hydroxide. Once we're in moles, we can use the stoichiometry in the balanced equation to go from moles of sodium hydroxide to moles of hydrochloric acid, because ultimately it's asking what volume of a hydrochloric acid solution. So in this case, I'm not going from reactant to product, I'm going from reactant to other reactant. Moles of sodium hydroxide on the bottom, moles of hydrochloric acid on top, and it's a 1-to-1 ratio as indicated by the coefficients. And then in the last step, moles of hydrochloric acid on the bottom, volume of hydrochloric acid on top, and this is given to me by the molarity of hydrochloric acid. Remember, 0.100 molar means 0.100 moles per liter, which is how I've arranged it in that last conversion factor. The last thing I have to do is plug this into my calculator. Remember, I'm multiplying everything across the top and dividing by everything in parentheses multiplied on the bottom. So I could plug this in a couple different ways. 25 milliliters of sodium hydroxide times 0.350 moles divided by 1,000 and then divided by 0.1. So I'm dividing by everything on the bottom. The other way to do it is to multiply by everything on the bottom, but just to make sure you're putting those values in parentheses. Either way, you should get the same answer. That answer is 0.0875 liters of hydrochloric acid. The other way to look at this is, we already said that neutralize means moles of acid equals moles of base. We looked at another equation where moles equaled moles, and that was our dilution equation. So if we're saying moles equals moles, we know we have to take the molarity, multiply it by the volume, and that also equals, again, the molarity multiplied by the volume. So this does take the form M1V1 equals M2V2. And in this case, we're just solving for the unknown volume, the same way we would in a dilution problem, dividing both sides by 0.1. And we get 87.5 milliliters. Now those numbers looked a little bit different, but in the last problem, the number was reported as 0.0875 liters. So those numbers are actually equal in terms of their quantity, they're just in different units. So the numbers are reported just a little bit differently. If you see the word neutralize, that word is very important because that tells you that you're looking at moles canceling each other out. So if you see the word neutralize and the reactants are 1-to-1 ratio, then you can use your dilution equation. So here we see they are a 1-to-1 ratio. So you can use the dilution equation here. If you do not have a 1-to-1 ratio, you need to use the stoichiometry and the balanced equation through just straight unit conversion to be able to solve this problem. The dilution equation will not work if you do not have a 1-to-1 ratio.